This section is a bit of a hodgepodge. If you look through the examples in the textbook, you'll see all sorts of material being covered. I've selected one representative type of problem that we're going to learn how to do. But that one type of problem breaks into two parts. And the type of problem I'm referring to is when we are integrating powers of the sine times powers of the cosine. And the cases I'm referring to are as follows. If at least one of these numbers is odd, then this integral is much easier to compute than if m and n are both even. So in this video, we'll look at the easier, I should put that in quotation marks probably, but the more straightforward of the two cases. And in the next video, we'll look at what to do if both the powers are even. So let's illustrate the method via example. Let's say we've got the seventh power of the sine times the fourth power of the cosine. And let's see how to find this indefinite integral. 7 is indeed odd, so we are in this case. Step 1 is to select an odd power. And in this particular example, there's only one odd power we could select. This is just something we have to do if both these powers are odd. And it doesn't matter if both these powers are odd, which one we select. So it's an arbitrary choice. Step 2. Pull one of the selected trig functions out of the power. I'm not sure how clear that is, but I hope that when you see it done, it will be clear. We take this seventh power and we pull one of the signs out so that we have a sixth power remaining. And this other trig function, the one we didn't select, we're not going to do anything with right now. Rewrite the now even power as a square raised to some other power. So the sine raised to the sixth power is the sine squared cubed. And this sine that we pulled out, we leave alone. And the other trig function, we leave alone. Now, use the Pythagorean identity to rewrite our square. In this case, it's the sine squared, and the sine squared is 1 minus the cosine squared. And at this stage, we have entirely rewritten the integral to be in terms of its cosines in this example. It might be sines in other examples, but we've rewritten this entirely in terms of one of the two standard most common trig functions, except for one, which we have from back in step 2, when we pulled it out. And now we proceed using U substitution. The point of pulling this out was twofold. First of all, pulling the sine out made this even, and ultimately let us convert it to cosines. It's also there to provide the du when we do U substitution. We're missing a negative sign, but we can stick a negative sign in as long as we put another negative sign out there. And this then is negative the integral of 1 minus u squared cubed times u to the 4th du. And this, at least theoretically, is an integral we can easily take. In particular, this is a polynomial, and we can integrate polynomials. The theoretically part of this statement comes from the next step. Polynomials can always be integrated, but only if they're in their standard form. And if you have a very high power here, like if we had a 20 or, even a 5 or a 7 or something, putting this in its standard form is not a quick piece of work. It requires a lot of effort. So we have to multiply all of this out. And I'm going to do most of this off screen, as it were. I FOIL'd these out. Now I'll multiply this by this, again off screen. I'll combine all like terms in this sum. distribute this u to the fourth through here. And finally, this is an antiderivative or an indefinite integral that we can take. And of course, u is a dummy variable. U is the cosine of theta. So in terms of the integral, we actually, or in terms of the variable, we actually want, let's also distribute this negative sign. 1/11 times the cosine to the 11th power minus 1/3 the cosine to the 9th power plus 3/7 the cosine to the 7th power minus 1/5 the cosine to the 5th power plus a constant. So that's our method. A few comments. First of all, I mean, if instead of the sine being raised to an odd power, the cosine was, it would be the same process. When we selected an odd power, we'd select the cosine, we'd pull a cosine out, and we'd just go through the same process. I phrased this in terms of powers of sine times powers of cosine. If we hadn't had a power of cosine, this whole process would still have worked. So we don't need powers of sine and powers of cosine if we just have an odd power of the sine, or we just have an odd power of the cosine. That still works fine. In the next video, we'll look at what I would characterize as a significantly messier case. What happens if the powers are both even?